The job of a compiler is to translate a program from one language to another, especially from a language like C to a language like machine code. And we say that that compiler is optimizing if it tries to analyze the program and specialize that transformation to make the resulting program run faster. When mapping to machine code, that means deciding how to use registers so that the machine will not have to go fetch values from memory more than necessary. Picking instructions that are faster or more compact. We've seen using LEA, for example, instead of sequences of adds. Getting rid of code that isn't going to run at all, that we call dead code, and eliminating other minor inefficiencies. An optimizing compiler doesn't usually change the asymptotic complexity of a program. So if you have a quadratic time algorithm, it's generally going to stay a quadratic time algorithm after it goes through a compiler. So that means that as a programmer, it's still your job to use a proper algorithm. Still, the differences that a compiler makes can be up to a factor of 10 in many cases. And sometimes the compiler can just do that automatically, and sometimes the way that you write your program affects how effective the compiler is. So the compiler is, of course, helping you by making your program run faster, but sometimes you can help the compiler as well. And that's much of what we'll be talking about today. In particular, there are certain patterns of programs that compilers generally can't see through, or they have to generalize in a way that you didn't intend. So the two big ones are memory aliasing, where two pointers refer to the same address, even though you as a programmer don't think they ever should, or calling functions that the compiler hasn't known about or hasn't gone and inspected in the context of where it's being called. So, for example, here's a program that sets x to 5 and y to 3 and calls setAdd twice. There are a couple of ways we could implement setAdd twice. The first way is to look up the value in yp and add it into xp and do that twice. And the second one, which you're more likely to write because it's simpler, is to look at the value of yp, multiply that by 2, and add it to xp. Now both of these may look equivalent, and in fact they'll produce the same results when we run it on that example at the top. But if we compile this to assembly code and go look at it, even when we're using optimize mode, then we'll see that the first one really does look into memory twice. It gets a value out of RSI and a value out of RSI again and puts it into RDI twice, the memory that RDI points at. Whereas the alternate implementation gets the value once. The compiler has chosen to still use adds instead of multiplies, maybe justifying that first choice of implementation in a way, but it only looks at memory once and then stores the result in memory once. And the reason the compiler has to preserve this difference is because those programs aren't actually the same. If we change the call to setAdd twice so that we pass the same pointer in for xp and yp, then these two programs behave differently. And we can see that by just trying it out. So instead of x and y, I'm going to have just x. And I'm going to pass x in. If we call the b version, so let's compile that to run the b version. We get 15 as we expected. We started with 5. We added 5 twice. If we call the a version, which was using addition to avoid the multiplication, we get 20 out, and that's because we take 5, add it to 5 and get 10, and then we add 10 to 10 to get 20. So the compiler is effectively aware of this difference, and it has to compile these programs in different ways. And the second one happens to be more what we were thinking about probably, but the compiler doesn't know which operation we actually had in mind in the case that xp and yp point to the same way. So that's why the way that we write code can affect the performance, the resulting machine code. That is, the compiler is generally limited. It's not supposed to change the program behavior. There's a particular reading of what that code was that it has to preserve. Sometimes the original program has undefined behaviors. In that case, the compiler is free to do different things. And that's why we sometimes see differences with dash O2 and not with dash O2. There are certain things that can be obvious to you as a programmer that are not obvious to the optimizing compiler. And in the previous example we just saw, that was a case of we wrote really two different things, that if we had thought about pointer aliasing, that we might have seen the different behavior. But in other cases it can be that you declared something to be a signed integer where really it's always going to be unsigned, or it's always going to be positive. And by choosing different data types, you can more precisely express what that program is supposed to do and help the optimizing compiler. On the other hand, if you don't do that, then the compiler has to make very general assumptions, like negative numbers are possible. Another thing to keep in mind is that most of what an optimizer compiler is going to do is confined to a single procedure. That's less true than it used to be. GCC will inline functions, and it'll use information from one function as it analyzes other functions that call it, but even that is generally constrained to a file, unless you use link time optimization, which is not the default anywhere that I know of. Then all of the specializations that a compiler will perform will be local to a file, and depending on the flags or the complexity of the programs, typically limited to a single procedure. Finally, the analysis that a compiler does is based only on what is in the original source program and not related to the inputs. So there are systems where you can monitor the execution of a program and keep information about what values actually flowed through, and adjust the program's compilation in that way. But normally that's not the way we do things. The optimizer doesn't know what values are going to come in as inputs, like on the command line or in files, and so it has to be very general with respect to all the possibilities.